So now I'm gonna open Phoenix. And I do the usual thing. We're gonna do new project. I'm gonna do a new worksheet. I'm gonna add the first column would be time. The units are hours. And then I'm gonna have another column will be concentration. The units are microgram per liter. And then I'm gonna have a column that his name is Bruce. Okay. So I do a copy. So I'm gonna copy. Oh, those I would say let's do that. We might do insert. I would call it just 1, 2, and 3. Or not. It doesn't matter. Maybe it doesn't matter. Let's see how it's working like this. Like this one, I want to make sure that now the first thing I'm gonna send to plot. So this is something you should document, all right? When you write your report, so the first thing you plot, and then you tell me what do you see, the first thing you see, all right? Something you might want to discuss. So you put X, Y, and those will be your group. And here we are, all right? So I see 3 doses, 5. Again, on linear paper, I don't see much. When I plot on the semi-log, then here I see something. What I see that the yellow is, look pretty much linear, but the other two, they show a little bump, all right? So definitely what I see is probably there is a saturation here. Now, when I go back to the worksheet and then I want to, so I know I want to go to the Michaelis-Menten. So I'm going to go send to, I choose the Nonlinear plastic modeling. And you see there is the Michaelis-Menten model, all right? So I click here. So let's see what they ask, just in case, all right? They ask the usual thing. I have to identify the time and the concentration, and we have a sort. Then we're gonna see the model. Of course, it's an IV bolus, so 301 is good for me. And then you see the number of constant. As I suggested, I'm gonna put you 3, all right? And then we see, because we see we have a constant here. The initial estimate, I want to use the initial worksheet, the dose, that is mine. And now, by default, it's giving me, the Nonlinear generated parameter, but if I use this one, it's going to crash it, give me error. We can try, but, So what we have to do user supply the initial parameter values. And I would suggest to use the Nonlinear bounds. So to do the user supply, so let's see, we need the volume of distribution, Vn and Kn. And the constant we said, the first constant is the number of doses, that is 1. The second constant is the dose, so we just copy. It's okay, no, 1, 0 too much. The third constant is the time, is administered at time 0. So now because 1 and 0 are the same, so I can do this. Now I'm gonna change the number. This is 32,000 microgram, and this is 640. Okay? But still, now with the initial estimate. So this is why I have Excel. All right. We can also go. I have my blackboard here. I'm gonna open the slides. So what we see from the Givaldi book, we're gonna do this, all right? We're gonna look. We're gonna look at this one. We're gonna do this, all right? So I have 3 data sets. In order to choose the estimate for Vmax and Km, I'm gonna choose the highest dose, because it's the one where the nonlinearity is more stronger, all right? So I'm gonna take this, I'm gonna insert a graph, okay? This is it. Even on the non, normal paper, you can see that this is 0 order, because the slope is perfectly linear up to here, roughly. Okay? So what I'm gonna do though, so I'm gonna do I have to plot, let's see. Okay, so, but I still wanna, yeah, let's plot the LM. Okay, so let's do this. So I'm gonna take equal the LM of the concentration. Okay. So I'm gonna take this one, and then instead of this, this is nice on Excel, all right? So now, when I see the data, plot the log, I say, well, I'm gonna take only the slope from the last 3 data points. So I'm gonna take the option not like that. I think I have the option. I'm gonna take the last 3 data points. And I'm gonna add the trend line and display on the. Okay, so this is my trend line. So what does it tell me? Tell me that the slope is 0.71. So I have the slope is 0.71. It should be if I want to do, you can put the unit here. Okay, and the intercept is gonna be, that would be, what is the intercept? Would be the log of C0 star, all right? So the intercept is 14.123. So C0 star is gonna be equal to the E exponential of this number. Do you agree? Okay. So at this point, let's go back. Well, okay, I leave it there just in case we need it later. So I'm gonna plot again the data, because I need the real C0 from these data. So I'm gonna plot again. from here, maybe I'm gonna do bigger so I can see. We have a 2500, this is, make it bigger and bigger. Let's say this is, again, these are initial guesses, so they doesn't have to be exact. Again, there is a difference between a 50 and a 5,000. But between a 50, 60, even a 50 and 100 is not a big deal. So I would say if this is 2,500, let's say they would be roughly here. So let's say 2,800. We take 2,800. So let's say that C0, the real C0, not C0 star, let's say that is 2,800. Okay, so if we go back in the slide, okay, from C0 and C0 star, I can figure out the Km. All right, so I just say that Km is equal to what? Is equal to, now I forgot. So
C0, C star.
is equal to C0. No, let me.
Yes.
I'm gonna see. Oops, no. Okay, so I can see. I don't want to make a mistake. So I can see the equation here. All right. So Km would be equal to C0. C0 is this one, right? So I click here, divided, open parentheses, ln of C0 star, that is this one, divided by C0. Close parenthesis 2 times, and so Km is 450, okay? What is Vm? So Vm, I'm gonna look at here. Vm
Km.
is equal to the,
Km.
okay, so Vm will be the slope multiplied by Km. So I go back here. So this one is gonna be equal to the slope multiplied by.
Did you have any problem with your door?
No, today no.
There was no one, right?
No.
The door was locked. So
The door was
you
locked.
want to keep it locked?
Oh yeah, you can have it.
Okay.
All right. So Vm is equal to the slope multiplied by Km, we said, all right? And here we are. And and now we are left with V. The volume of distribution is going to be equal to the dose divided by C0. So the dose will be this one, so this will be equal to the dose divided by the real C0, all right? That will be this one. And I find the volume is 11, all right? So these are now my initial estimate. So I go back to Phoenix, let's put it here so I can see it, or I can write on a piece of paper, all right? So I go back to Phoenix, and now I have all the, it's the same drug, so it's going to be the same enzyme that is responsible for the nonlinearity. So it's very likely that the volume of distribution, Vm and Km, are the same. I don't have to re-estimate for every data set, all right? I can just use the same. So V, we said, let's say that is 11, all right? I don't have to go by all the digits, all right? It's just an initial estimate. Vm is 320. Km is